All right. So operational laws. There are, just like Little's law, there are 5 other laws that apply under very general conditions with very little assumptions. And Dunning and Busan came up with these laws, and these are actually the ones that are very useful and powerful because they don't make many assumptions. So you don't have to worry about whether this is exponential or not, and so on and so forth. So we call them operational laws because these do not require any assumption about the distribution of service times or inter-arrival time. Just like Little's law doesn't assume that that is exponential or anything, it just applies. You just measure the times in the outside the system, and you can find out how many people are inside the system. And so they're directly measured. And so they are operationally testable assumptions. So something is operationally testable, it means even a person who is running the system can measure it and see whether this is applied or not. So that can be verified by measurements. Something that cannot be verified by measurements are independence and things like that, right? So, for example, whether the number of arrivals is equal to the number of completions, anybody can verify that. So we make an assumption. Remember, one of the assumptions in Little's law is that nobody is killed, and you can very easily verify that. And yeah, but whether it is independent or not, you cannot test it. Independence, even if you sit down for years and you cannot test it out that this is independent or not, because that is just a statistician talk about it, make that assumption all the time, but they cannot verify it. So that is not operationally testable, right? So then we have a number of things that we want to relate, and let's just introduce that notation. And okay, so first is observation interval. So you sit down and system is a black box for you, and you observe it for t seconds. In that t seconds, AI jobs arrive and B and CI jobs leave. And the system is busy for BI times. Now, system could be a component like a disk, or it could be a whole system like a computer system. So the arrival rate then is number of arrivals divided by time, AI upon T. The throughput is number of completions divided by time, CI upon T. The utilization is busy time divided by total time, BI upon T. And the mean service time is how much the system spent on each of those jobs that completed, is total time served, which is BI, divided by number of served CI, BI upon CI. Clear? So the first thing we could say is that utilization is busy time upon total time, BI upon T, which could be written as CI upon T times BI upon CI. And so this is the throughput, completion divided by the time, CI upon T. How many jobs completed in time T? Times how much the time was busy divided by completion time. So that is throughput times the mean service time. So utilization, if you know the throughput of a system and you know the mean service time, you can calculate utilization. And we will use this notation, XI for throughput and SI for service time. I is the ith system, basically. Because we might have many devices in a system. So for ith device, the service time is SI. The throughput for the ith device is XI. If I know that, then I can calculate the utilization for the ith device UI. And this is true regardless of any distribution, any independence, dependence stuff. All you need to make sure that you know the completion and the time and so on and so forth, which you can measure. So these laws are similar to the Newton's law of motion and other things, acceleration, because these things are valid under very general conditions. And so in physics, we have those laws, but here in computer science, now we have these laws. Okay. So if I told you to use utilization law, this is the law. UI is equal to XI SI. Here's an example. Consider a network gateway in which the packet arrives at the rate of 125 packets per second, and the gateway takes 2 milliseconds to forward each packet. So we know the SI, 2 millisecond is the SI, and we know the arrival rate XI, because arrival is equal to entry in this case. So 125 is XI. You multiply those two numbers and you get 0.25, that's utilization. Now this utilization is valid for any arrival process, whether it is Poisson or exponential or Langian or hyper-exponential. Regardless of all that, this thing is valid. Yeah. X is equal to the 125? Yeah, because basically that's what it says is that arrive at the rate of 125 packets per second, and the gateway takes them forward. I mean, basically you're saying that it doesn't say that they are 125 packets leave per second. But basically, yeah. So that is the thing, is that we are assuming that nothing dies inside. So whatever comes goes out. Okay. So this is an example of first of the 6 laws that we're going to talk about. Second law is called forced flow law, and it relates the system throughput to individual device throughput. So this is the whole system, and inside it there are some devices, and we don't know how the jobs are going. I mean, they could be going any other way. It doesn't really matter, actually. So one could be CPU, one could be the system disk, one could be, data disk, and one could be network, and so on and so forth. Many devices in that system. And we can measure outside how many jobs came in. They basically came in. C0 came in, C0 got out. And if we were inside the system, we could calculate that the CI came to this disk and they got out. And then we could see how many times the job came to this device. So we can measure several things. First is, we measured that the devices have AI arrivals and CI completion, which are equal. So nothing stays in the device forever, right? So job flow balance, that's the assumption we are assuming, that nobody is killed. The second thing is each job makes VI request for the IF device. So when a job comes in, it goes to the disk 5 times or X time, and that is the number of visits. So CI equal to the number of visits to the IF device equal to C0 times VI. C0 is the number of jobs coming in, and then each of them makes VI visits, and therefore the total visits to that device is C0 times VI. Or other way around as well, VI equal to CI upon C0. This is called the visit ratio. System throughput is clearly given. If you measured for T seconds and you found that the C0 jobs came in or left, then the throughput is C0 upon T. The device throughput is CI upon T, and CI upon T is equal to CI upon C0 times C0 upon T. That means the device throughput is X, C0 upon T is X, times VI, and the CI upon C0 is VI. So XI is equal to XVI. This is the forced flow law. Basically, all it is saying is that the flow through the device is equal to VI times the flow through the system. All right. Any question on the forced flow law? None. Then we have to come to a very important concept called bottleneck device. And so if you combine the two laws that you have learned, then you can say UI, the utilization of the device I, is equal to XI times SI. This was the law before, right? Now we can write down XI equal to XVI. Then we can combine these two terms into DI. So DI is this product of VI times SI. So now we have a new relationship. UI is equal to X times DI. X is the system throughput, and DI is the total demand on the IS device. What it is saying is that on each visit you use SI, but you make VI visits. If you multiply the number of visits with the time that you used on each visit, You get the total demand on that IF device. That is DI. And so the utilization of the IF device is equal to X times DI. That means utilization is proportional to the total demand. All right, and this is an important observation because now one of the things that you want to do in every system is find the bottleneck. That is the one that is key to the performance. And what is bottleneck? Bottleneck is the one that has the highest utilization. So if you have three devices, one is 10% utilized, one is 15% utilized, and one is 25% utilized, the bottleneck is the one that is utilized at 25%. Even the 25% doesn't sound very large, but anything that has the highest utilization in the system is the bottleneck. That is the device on which you want to put your money on. If you're not happy with the performance, then the first thing you replace is the bottleneck device. All right. If you replace the other things, it will make very little difference or no difference. So if in your system, disk is the bottleneck, buying a faster CPU will make no difference. All right. And that is usually the case, that the disks are the bottleneck. All right. So first thing you need to buy is SSD. If you're not happy with the performance, replace the bottleneck. Alex, how do you find the bottleneck? By this formula, it says that all you need to know is you don't need to know system throughput. It doesn't matter what the system throughput is. All you need to know is the total demand that each job makes on each of the devices. Then you compare them and you know which is the bottleneck. All right, let's take an example. In a time-sharing system, a counting log produces the following profile for user programs. Each program requires 5 seconds of CPU time, makes 80 I/O requests to disk A and 100 I/O requests to disk B. And the average user think time was 18 seconds. So this is the 18 seconds here, user think time. Now let's just write down the numbers at this proper place. So 5 seconds of CPU time. So this is the 5 seconds right here, the CPU. 80 I/O requests. So there are 80 requests here to disk A. And 100 requests to disk B. So there is 100 requests to disk B. Then you notice that from the device specification, it was determined that disk A takes 50 milliseconds to satisfy the I/O request, while disk B takes 30 milliseconds per request. So we multiply by 50 here and multiply by 30 here. So we find out the total. So this is the VI, this is the SI, multiply them, we get the DI, total demand. Similarly, this is the VI, visit ratio, and this is the SI, multiply them, we get the total demand. Here, we could do the same thing, but basically there is only one visit per job. So 18 seconds comes out right there. And here the total is already given, product is already given 5 seconds. All right. So what we have found is with the 17 active terminals, the throughput was observed to be this X value. So what is given here is D CPU is 5 seconds, VV is 100, VA is 80, Z is 18, SA is 0.05, SB is 0.03, N is 16, N is the number of jobs in the system. XA is 15.7 jobs per second. This A throughput is given. Okay, so what can we do with these numbers? First thing is, and we repeat those things here so that you can see them again. So the first thing is that the vCPU is VA plus VV plus 1, because you have to go 1 times here, you have to go 80 times here, you go to 100 times, you have to go to the CPU 181 times. So that is the vCPU. dCPU is 5 seconds. So we could calculate, if we wanted to calculate the service time per visit, but there are 181 visits totaling to 5 seconds. For DA is 4 seconds because there are 80 visits, each 50 milliseconds. So that is 4 seconds. And DB is 3 seconds. So now we have 3 Ds. What is the, well, before I go to the bottleneck, let's go to the forced flow law. That's the system throughput. So system throughput, the first flow law says that the XA is equal to VA times X, or X is equal to XA upon VA. XA is 15.7, VA is 80. So the system throughput is 0.1963 joules per second. Okay. So, and then you can calculate the X CPU by X times V CPU. X is 0.1963, V CPU is 181, 181 visits per job. So that is the throughput of the CPU, 35.48 requests per second. For the disk B, XB is XVB. So you do the same thing, multiply, and you get that. And then you can calculate utilization, because utilization of the CPU is X times D CPU. X is given and D CPU is 5, so it is 98%. UA, the utilization of disk A is X times DA, which is 78%. And utilization of B is 58%. Now, just go through once more through all these things and see if they make sense to you, all these calculations. I remember that first time when you look at these, you can't remember all the formulas. But only 2 formulas so far, by the way. There are not that many. We are going to give you 5 more. But there are 2. UI is equal to XI SI. And then we said XI is equal to X times BI. Those are only 2 formulas we did. Okay. Total 2 formulas. And with those 2 formulas, we could do all this. We haven't used little psi yet. We haven't used it, but we gave you that formula, but we haven't come to that one yet. All right, so 2 formulas, and you can remember and I can remember. UI is equal to XI SI, and X is equal to XI equal to X times VI. Okay, those are just 2 formulas that we used. And particularly if you want to do it on the back of the envelope, you kind of have to remember this, because if you're sitting in a restaurant and somebody asks you a question, you can do this in the back of the, you're not going to have, my book or anything else. You just say, okay, all right, let me go and check this out. All right, so these are things that are very easy to remember. Just like I said, Little's law, you remember lambda is equal to NR. You have to remember these 2 laws. No, you're already getting it wrong. U is equal to X times DI, which was, you can go back and see the law. I can write it on the board too, but U is equal to X times DI. UI is equal to X times DI. And the second one was, it is already given here. U is equal to X times DI. And the second one was this one, which is XI is equal to X times VI. Those are the only 2 laws. All right. So given this, now we can calculate this thing. But most important, and here is the homework. And it's very simple, basically. I have put it here. You can fill it out and figure out what is the bottleneck device. All right, I will leave it this one and move on to the next law. Now, this is a bit of a complication that, let me see if I want to go through it or not. And this is not really necessary, but if you are doing real queuing theory, real queuing theorists don't use visit ratios. They use probabilities. And so when we are saying that out of 181 visits, you go to the terminal 1 times, the queuing theorist will say the probability of going to the terminal is 1 upon 181. They use what we call transition probabilities. Similarly, they will say that for disk A, the probability is 80 upon 181. All right. And disk B is 100 upon 181. So they use probabilities rather than the visits, which are identical. Basically, if you go to, I have asked you to measure the probability of going to disk A, what will you do? You will go and find out how many times something went to disk A and how many times it went to CPU, and then what is the probability, divide one by the other, right? So instead of saying 80 out of 181, they will say 80 upon 181. So that is what it is that visit ratios are equivalent to probabilities. Probabilities have to add up to 1. Once you get out of the CPU, you really have to add up to 1 here. And then you can calculate one from the other. And the formula for calculation is that you find out the total visit ratio for the device. In this case, the disk and the CPU is V1 is equal to 1 times plus V2 plus V3 plus Vm, which was 181. And then the probability would be basically, the number of visits divided by the total visits. Or if you had the probabilities, then you could calculate the visit ratio other way around as well. If suppose I gave you the probability is 80 upon 181, then you could calculate what are the visit ratios. Simple math actually, but we will not use visit ratios. We will not use probabilities, so forget that one for the moment. Here is an example of the same thing actually, is the transition probabilities, is that I'm giving you these probabilities. P1A is equal to 0.44, P1B equal to 0.55, P10 is this probability is 0.05. So what are the visit ratios? Basically, I've given you these three numbers. You divide it by the outside going outside, that would be number 1. And therefore, you got 80 and 100 as before. All right. So now we come to Little's law. Little's law says that mean number in the device is equal to arrival rate times the mean number in this system, mean time in the device. Now, so this is mean number in the device is Qi. And by the way, we are using only English letters here, not Greek letters. Real queuing theorists use Greek letters. All right. So, you know the difference. And the whole operational analysis does not use any Greek letters. That's why instead of saying n is equal to lambda r, which was the original Little's law, we are saying q is equal to lambda r. Q is equal to, actually, q is equal to xir, xr. Actually, we are going to say q is equal to xr, not lambda r. And so the Little's law is qi equal to xi times ri. Qi is the number in the queue, number in that device, equal to the throughput of the device times the response time in that device. All right, so this is how we will write the Little's law. So now with this new knowledge, we can do a lot more on that previous example. Rest of it is all before, so I'm not going to repeat all this, but this is exactly the same example that we have been going through. 80 visits, 100 visits, 1 visit, 17 systems, and everything else. So we know the device throughputs, X CPU, XA, and XB. Now, somebody tells me that they measure the queues, and the queues are 8.88, 3.19, and 1.40. If you know the queues, then we can calculate the response times, because the response time is equal to Q upon X by Little's law. So Q is 88, throughput is 35.88 here. So the response time for the CPU is 0.25. Response time for the disk A is 0.2 seconds, and response time for B is 0.07. So what are the response times? Basically, this is how long it takes for each visit to the disk A. Whenever you go to the disk A, there are two things you have to do. One is you have to wait in the queue, and then you have to get served. Previously, when we said SA, that was 50 milliseconds, that was the service time. Right? But now we are saying that the total time when you enter to when you get out, the total time is 203 milliseconds. That is the response time. Response time is entry to exit. But the service time is only 50 milliseconds. All right. Similarly, for the CPU, the service time I forget, but basically the total time when you enter the CPU and get out is quarter second or 250 milliseconds. Only for disk B. All right. Everybody understands the difference between response time and the service time? right? Service time is what time you spend at the server, or the server spends on you, and the response time is and includes the queuing time. So now we have a next law, which is called the general response time law. And so suppose we use the central server model, the one that this is even simpler than server. Central server model that the Busan invented. Then Q is equal to XR. The total number in the system, inside this system, is equal to the throughput times XR. This is basically applying the Little's law to this part. So if you just look at this part, then the total number inside this is equal to X, which is the throughput of this system, times the response time inside the system. Right? Now the total number in the system is equal to the queues at each device. So if you have M devices, total number will be Q1 plus Q2 plus Qm. And the total XR will be equal to X1 R1. So what we are saying is that if R1 is basically, this is what it is saying, Q is equal to XR, Q is this, and XR is basically sum of all the XRs. And I have to just explain that in the next slide. And therefore, if you take this, if you assume that that is the thing, then you divide by X and you get R is equal to X1 upon X. X1 upon X is V1. Now think about it, why that is X1 upon X is V1. So you really need to read this chapter very carefully. I'm going a little bit fast here, but I think this is actually anyway stopping point. But if you have read it very carefully and you would have done it, then you would know that that is the second law that we talked about. X is equal to Xi Vi. Right? So X1 upon X is equal to V1. X2 upon X is V2. And X upon V1. So basically, whole system response time can be calculated by multiplying R1 by V1 plus R2 by V2 plus Rm by Vm. So this is actually can be easily shown to be true. Why? Because you look at this system here. We look at the system. We made 80 visits to the disk A. Right? And each visit took 203 milliseconds. Each visit took that much, right? So we multiply 80 by 203 milliseconds. Plus, each job also had to go 100 times here, and each visit took point this. So we multiplied this number 71 by 100, and each job had to go through 181 times through the CPU, and each time it took this much. Multiply by that. You multiply by those visit numbers, you will know the total time this was spent inside the system. That is your total response time. All right. And that's all we are saying here. We are saying the total response time is equal to the visits to the device 1 times the response time at device 1 plus visit to the device 2 times the response times at device 2 plus so on. Okay. And so this is general response time law. General response time law is R is equal to Ri Vi. Now, all of these are simple, straight mathematics. I mean, there's no assumptions here. There are no assumptions. Just, I mean, if regardless of what happens, if you know the visit ratios and you know the response times, you can multiply them and add them. All right, I will still stop here. What I wanted to say was, yeah, I think this is probably it. The next thing is the example of this, and maybe I should finish that so that I can give you the homework B. Okay. So the example is same thing that we have been working on, and all we do is R CPU, V CPU, RA, VA, and we can get the whole thing multiplied together, and we get 68 seconds as the system response time. That's all we did. We just use R is equal to R CPU, V CPU plus RA, VA, RA, VB. And that's all I'm asking you in homework 33B. Homework 33B, you just have to find the visit ratios, and I've given you probabilities here so that you can also practice with how to convert the probabilities into visit ratios. Once you get the digit ratios, you have to calculate the response time, and then you can calculate the total queue length. All right. So actually, this is already, the steps are already given. All you have to do is fill in the blanks.